Hey Adventers, welcome back to our spoiler-free Advent of Code 2024 series. And yesterday it was super fun trying to solve that Easter egg. And today we are going to tackle day 15. Here is a trivia for you. Do you know what is a 15-sided polygon called? And well, if you said a pentadecagon, you would be absolutely correct. And this is why today my face cam is shaped like that. And if you're new here, hi, I'm Jatin Kumar Malik. I am a principal software engineer who absolutely loves solving these puzzles. Last year, I did a blog series on Medium, and this year I'm doing YouTube because I just feel it's way more interactive and probably will allow you to understand the problems a lot more better. And if you haven't checked out the last 14 days, here is my playlist. Feel free to go through them. And trust me, once you understand the logic behind approaching a problem and solving a problem, the coding part becomes much, much simpler. And I hope you will also get to learn something new. But with that, let's kickstart day 15 and let's read the problem. So the problem today is called Warehouse Woes. You may appear back inside your own mini submarine. Each historian drives their mini submarine in a different direction. Maybe the chief has his own submarine down here somewhere as well. And if you don't get the reference, we are still looking for chief historian from day 1. And I'm trying to help the elves find him so that we can save Christmas altogether. So you look up to see a vast school of lanternfish, and this is a reference, if I'm not incorrect, this is a reference to 2021 day 6, swimming past you. On a closer inspection, they seem quite anxious, so you drive your mini submarine over to see if you can help. Because lanternfish populations grow rapidly, they need a lot of food, and that food needs to be stored somewhere. That's why these lanternfish have built elaborate warehouse complexes operated by robots. That's interesting. These lanternfish seem so anxious because they have lost control of the robots that operate on some of their most important warehouses. So we have few lanternfish. So I like writing things down. Lanternfish has their own warehouses. And what we understand is that these warehouses are operated by robots. It seems like we have been dealing with a lot of robots lately. And it seems like they're anxious because they have lost control to these robots. And it is currently running amok, pushing around boxes in a warehouse with no regards for lanternfish logistics or lanternfish inventory management strategy. So it's basically a chaos. And let's read more. So right now, none of the lanternfish are brave enough to swim up to an unpredictable robot so they could shut it off. However, if you could anticipate the robot's movement, maybe you can find a safe option. I see. So they are just running around in some directions. The lanternfish already have a map of warehouse and a list of movement the robots will attempt to make. That is our puzzle input. And the problem is that the movement will sometimes fail as the boxes are shifted around, making the actual movement of the robot difficult to predict. Interesting. So our puzzle input is given as a map of warehouse, and then we are given a list of movements of these robots. So we are given an example. Let's get this in our CodePad whiteboard and then see what we are doing here. So that we can iterate on top of that. And then we are given a bunch of these values. So I'm not copying them, but I'm going to refer them from here. So these are the movement of these robots. So let's see how it works. So now as a robot attempts to move, so a robot here is denoted by @. So we can see the @ means it's a robot as a legend. And there are boxes. So all the 0 represent boxes. So as the robot attempts to move, if there are any boxes in the way, the robots will also attempt to push those boxes However, if this action would cause the robot or boxes to move into a wall, so this hash, the boundary, the hash or pound sign is our wall, which is in the boundary, but we can see there are some walls in between as well, as we can see here. And then there are some walls here. Okay, so the idea is that a robot, if it starts moving, let's say this example, if it start pushing this box will come and line up against the wall and then it will stop moving. That makes sense. So the initial position of these are shown on the map at the top of the document the lantern gave you. So in our puzzle input, I'm assuming it looks something like this, where we have a map and then we have a list of movements. The rest of the document describes the moves, where we have this for up, for down, for left, and for right. So we have 4 directions for a robot, as we mentioned here. So 4 directions, and the robot will attempt to make. So because some movements may not work, but we'll talk about them. And in the same order, the moves form a single giant sequence and they are broken into multiple lines just to make copy pasting easier. So the values that are given here, it's basically a single continuous set of instruction for all the robots, I assume, or it seems like there is only one single robot, but that may change. But that is the point that I have noted right now. And let's read more. The new lines within the move should be ignored. Yes. So here is a smaller example to get you started. So let's look at that and then we will come back. So I have copied this example, the smaller example that was given to us. Let's track the robot's movement with pink color here, pink, red. And here the robots would attempt, given the sequence of move, it would push around the boxes as follows. So we can see it is starting from here. In the first position, it will try to go left, but that will not work because there is a wall. So nothing will happen. In the next move, it will go up. So the robot will go up. The robot will come here and it will go up again, but it cannot go up because there is a wall. So then it will try to go right. So when it go right, the robot will come here and it will push the wall to come here. And then it will push right again. So now this is an interesting question. If we have 2 boxes and it seems like there is an edge case, what happens? Is the robot powerful enough to push the boxes? I think so, but we can check here. So the robot was here, it moved up, and now it moved up and it pushed the box. So we are currently on this position, if you can see. And then it tried pushing it again, where it pushed both the boxes. So it seems like if I go back, yeah, so our robot comes now here and the boxes come here, which is this. And this is done. And then it will try to go right and right, but it won't work because there are 2 boxes and a wall. So that won't work. And then it wants to go down. And when it goes down, you can see there are 4 boxes below. So when you go down here, it will come here and it will push these boxes. So a new box would come here. And I think we can see that here. So all 4 boxes are now touching the wall. And then the next down instruction will be ignored or will be useless because now there are 4 boxes stacked against the wall. Then it will go left. So it will come back here. And then it will go down. So it will come back here. Then it will go right. So it will push this box. So it will come here. It will push this box. And then it will go again right. So the box will come here and the robot will then come here. And we can see that here. So we are currently at this case where the robot is pushing and now it is facing the wall. And now it will go down. So the robot was last here. So it will go down. And then it is going left twice, which means there is a box here. So in the first position, it will push the box. Robot will come here. The box will come here. But in the second position, it will not be able to push it because there is a wall. And then we are at the end of instruction. So the final position of our robot is somewhere here after following this series of these instructions right here. And that seems like our final position. Yep. So there is a box with next to the wall and our robot is here. So the larger example has many more moves. And after the robot has finished all those moves, the warehouse would look something like this. So I'm not simulating all of them. You're welcome to try, but we can see that it is mentioning after we have executed. I'll show you the moves. So yeah, we can see that it is showing that for this example where we had a lot of these moves that are given here. So let me align this like this. The final result would look something like this, where our robot's final position would be this, which is 1, 2, 3, 1, 2, 3, 4, which is 3, comma 4. So now let's see what do we have to do. So this is it's a very interesting problem where we are pushing bunch of boxes and then we cannot. So there is some kind of a look ahead that's going on. But let's read what do we have to do now. So the question says that, I'll push it here and let me grab my pen. Yeah. So the question says that the lanternfish uses their own custom goods positioning system, which is GPS for short. Where have we heard that before? To track the location of the boxes, the GPS coordinate of a box is equal to 100 times its distance from the top edge of the map plus its distance from the left edge of the map. So if you are given a box that has coordinates x comma y, I'm just following the basic matrix system where this is 0 comma 0 and this is m comma n. So for any x or y, if you have to get its GPS coordinate, you will have to calculate the 100 times the distance from top edge of the map, which is our this distance, which is nothing but the number of rows, and you will add that to plus its distance from the left edge of the map, which is our this number here, which is the number of columns, which is the x. So it would be x plus 100y. So it seems like we have a lot of linear equations right now. And this will give us the GPS coordinate of the box that was given to us. That makes sense. There is a double O here. Yeah. And this process does not stop at wall tiles. It measures all the way to the edge of the map, which means we will count that as well, which I think we already are. So 3 comma 4, if for this was the position of this, but let's consider maybe like this one. If you have to calculate its GPS coordinate, this is 1, 2, 3, 4, 5, 6, comma 1. So 6, comma 1. And if you have to calculate the GPS coordinate, it would be 6 plus 100 into 1, which is 106. And I'm sure they would have given an example here. So the box shown below has a distance of 1 from the top edge of the map and 4 from the left edge of the map, resulting in a GPS coordinate of 100 into 1 plus 4, which we can see here. It is 1, 2, 3, 4, and then 1. So it is 4 plus 1 into 100. They have just written it the other way around, but it is still following the x plus 100y equation. So now what lanternfishes would like to know is they would like to know the sum of all boxes' GPS coordinates after the robot finishes moving. In the larger example, the sum of all boxes' GPS coordinate is 10092, and in the smaller example, the sum is 2028. I see. So what we want to do is that, like just like we calculated the GPS coordinate for one of this box right here, which was here, after the robot is done doing all the n moves, we want to take each and every box and calculate their GPS coordinate and then do a sum. So the final answer for us would be sum of all box dot GPS coordinate. Like maybe if we have a function like this, we will do that. And before that, we have to, of course, do the simulation. Okay, so the question is saying predict the motion of the robot and boxes in the warehouse. And after the robot is finished moving, what is the sum of all box GPS coordinates? And to begin, get your puzzle input. And if we see our puzzle input, we can see that on this half, we are given the initial starting grid. And then on the bottom, we are given multiple moves. And I just want to make sure that we are dealing with one robot. Yeah, so we can see like I tried searching for @ and we only have one match, which is right here. So we just have one robot, lone robot, trying to move into this maze. And it reminds me of that popular Disney movie called Wall-E, if you have seen it. But yeah, with this, I think this is a good time for you to pause the video. And I hope I was able to explain the problem well. So pause the video right now, grab a paper, pen, open a whiteboard, and try to think that how would you model this problem and how would you try to solve it with code. And once you're back, we will discuss some of the initial hints and initial approach that I'm thinking about. So see you in a bit. All right, welcome back. And you can see that we have received the gold star for the part one. And I followed the exact same approach that we discuss below in the hints about following a simulation and then calculating a sum. One interesting challenge I faced while handling the box logic was to make sure that when a box is pushed, it would not collide with another box. And to do that, I recursively took that box if in the same direction where we are pushing the box, and if there is the next cell is a box, I just took that and recursively checked if the next cell for that in the same direction was empty or a wall. If it was a box again, and then I would go on till I see that either it is empty or it is a wall. If it is empty, then I would recursively call back and then move each thing ahead by one position, and then at the end move my robot ahead. And if it was a wall, we would just do nothing and we would just exit out of the whole chain. So this was an interesting approach where we were in a way looking ahead by n number of items based on some kind of specific rule, and I used a lot of early returns to make our code a lot more simpler. After simulating all the moves, I just iterated through the grid, found all the boxes' final position, and calculated the sum of their GPS location, and that's all. I will push my well-documented code below to the GitHub, so make sure to check it out if you're still confused about the part one. But with that, let's move on to the part two and see what we have to do. So yeah, the part two. The lanternfish use your information to find a safe moment to swim in and turn off the malfunctioning robo. Just as they start preparing a festival in your honor, report starts coming in that a second warehouse robot is also malfunctioning. Oh, so it seems like there is another warehouse. This warehouse layout is surprisingly similar to the one you just helped. There is one key difference, that everything except the robo is twice as wide. So there is another warehouse which is twice as wide. Interesting. The robo's list of movement does not change, so we still have 4 directions where you can move the robo. And to get the wider warehouse map, you start with your original map, and for each tile make the following changes. So we have to double take the initial input and widen it, like basically increase the columns by twice. And how would we transform the existing map? So we are given some of the cases. So if the tile is a pound sign, then the new map will contain 2 pounds instead. Okay. If the tile contains a box, the new map will contain this instead. And what is this? We will see. And then if a tile had an empty space, it will now have 2 empty spaces. And if the tile had our robo, since the robo is not twice as wide, robo stays the same. As it mentioned in the question, it will become a robo with an empty space. And this will produce a new warehouse map which is twice as wide with wide boxes that are represented by this. So now this is like a new type of box which is twice as wide. So this is a wide box. Okay. And it again mentions that the robo does not change size. So the larger example from above now would look like this. So if I get it here and I'll paste it. So we can see that we just transformed the original one. If I copy this and I go back here. Yeah, so this is now it is represented. This was the example from part 1. And in part 2, when we do the whole 2x wide thing, this is how it will look like. And each box is now converted into a double square brackets, which is like our wider box. So how does it change our pushing logic? Let's see. So because boxes are now twice as wide, but the robo is still the same size and speed, boxes can be aligned such that they directly push 2 other boxes at once. For example, consider this situation. So we are given a situation where we have a robo and we had this. And after appropriately resizing the map, now robo would push around these boxes like this. So I think we can draw like some of the cases that would be interesting here. So we can have a case here where I think you have 2 boxes like this, and you have your robo here and you're pushing them here. So now it will push these 2 boxes, granted that there is enough space, because remember now each box takes 2 space. So you will move it, and even if there is 1 space, you will still move it by 1 space at a time. So Yeah, so even if it is 2, look, you can still move it by 1, where it would now become something like this, if I had to tell, like by 1 space. And then we can have more cases where I think it is pushing it on the left and then going down and then going down and then going left and then going left. And now this is interesting where it is going up. So it seems like since now the boxes are wide, like whenever you are pushing a box, in the part 1, we were just checking for one cell ahead of it. But here we will have to check both the cells in the same direction, and they can have more than one boxes. So there can be 2 boxes directly touching the box. So the example that we are given here is very interesting, where it is a scenario where there are 2 boxes and then there is 1 box that is here. And this is our robo at one of the box, because remember, like it is occupying 2 spaces, but robo is only occupying 1 space. And then if I had to represent this nicely, it is something like this. And we are given like an empty row on top of it, and then maybe there is a wall. So now in this case, if my robo has a direction of this, it will be able to push like this 1, 2, and 3 boxes up, which it is doing here. So if you see here, I drew exactly this. And even if it is pushing from the right end of this white box towards the up direction, it ends up pushing all 3 boxes. And interestingly, when it pushes all 3 boxes, and if there is a wall here, it cannot move forward, because if it pushes this and it tries to push this, this is stuck. So initially the collision, and this changes a lot of things in our code. Initially we were just checking one cell ahead in the direction recursively when we were peeking ahead and looking ahead to understand if there is a valid move or not. In this case, your valid move can be from anywhere from 1 cell to 2 cell to 3 to 4. In this case, as you can see, we are checking all 4 spaces if there is an empty space or if there is a wall. And I think moving ahead, if we see like it tries to move up, it cannot, it moves left, it goes up. And then if it tries to push this box from this direction, it just moves without impacting other boxes. So this case is interesting, where you have 3 boxes like this, but now your robo is trying to push from this direction. So when it tries to push from this direction, your robo will come here and your box will come here in the next step, which I think is happening here, and it is moving that. And then again, if you move up and if you are just touching one single box like it is doing here, it will only move that specific box. So very interesting. So this warehouse also uses GPS to locate the boxes. And for the larger boxes, the distances are measured from the edge of the map to the closest edge of the box in question. So what it is saying is essentially, if you are given a box, your GPS coordinate will always be used from the leftmost part of the box, because remember, it is taking up 2 spaces. And we are given an example. So there is an example here where there is a box shown that has a distance of 1 from the top and then 5 from the left edge of the map. So 0, 1, 2, 3, 4, 5. So this is this left square bracket coordinate is 1, 5. And then we just multiply 100 into 1 plus 5 and we get the GPS coordinate as 105. So in this scaled up version of the larger example from above, after the robots have finished all of the moves, the warehouse would look something like this. So we are again given the final representation of this map. So this was our initial map after doubling the size. And then when the robots have finished making their end moves, it finally looks like this. And some of the boxes of this GPS coordinates is 9021. So we are given that. And now what we have to do is we have to predict the motion of the robots and boxes in this new scaled up twice as wide warehouse and find out what is the sum of all boxes of final GPS coordinates. So very interesting. It seems like on the surface, not a lot has changed, but I can clearly see that under the hood, our logic of how we were initially operating in part 1 will have to be modified in a very interesting way. But with this, I think this is a cue for you to pause the video here and think about what are the changes that you will make in your part 1 solution to make it work for part 2. And once you're back, we will discuss some of the hints and some of the approach that I am currently thinking about modifying, and then we will compare our notes. So see you in a minute. And yeah, if you're looking for a hint, let's talk about that. So I'll just make some space, pick our trusty old orange color. And in terms of hints, what I can think of is that you need to, this is very much related to this. So after you have transformed your input map, you need to see like how much part can you reuse from part one solution and the logic. The main difference now is that how you handle the white boxes in your code. Most of the other logic, the movement of robot and the map would remain exactly the same. And I think the one thing you need to ensure when you are doing the 2x, handle the robot position carefully. I think that is something where a lot of people can make mistakes, because when you are replacing that based on how you are doing the 2x, you need to replace it with a robot position at the rate and an empty space on the right. So the robot would still be on the left of that replaced location. And I think another thing that I can think of is while simulating moves, I think that is the crux of the whole question. You need to check the peek ahead method and the look ahead method. You need to ensure that how would you look for collision with the white boxes. And you will need to consider the both cells occupied by a box at first level, but based on what direction you are going in, if there are more boxes touching either of the sides of this white box, so as we saw an example in a case like this, and if your robo is here trying to push down, once you look ahead for this box, for the position, if I had to check this, once you check that this and this position, if you find a box on any other position, similar to part one where you are recursively passing the position of just that box, in this case, you will have to pass both the position of that box if you find one of the square brackets, which is one of the part of the white box. And when you pass that and you are looking for the same direction, you will again look for both the adjacent positions. And if you again find a part of a box, you will have to pass that on. And when your recursive chain returns, and let's say if there is an empty space below, you will have to move each box by its position, one position in that direction, and then move the robot. And I hope this helps. I think this is the most important part of the question. And I think similarly, like when you are checking the block, even if one of these positions is blocked, let's say if there was a wall here, that will block the whole chain and your whole movement will not happen. And once you consider that in your simulate function, it should be fairly straightforward for you to do a dry run on this example given here below and check if your test case passes for the answer of 9021, and then probably extrapolate the input.txt and try to work on how you're going to 2x the input and try to find the answer. And yeah, with that, I'm going to write some code. Probably you should also do the same. And this seems fairly exciting because I'm not too worried about this part, but this simulation part where we are doing a peek or a look ahead, this logic is very interesting to me because it is in a way, if you see the logic of looking at connected neighbor problem, but the interesting part is your neighbor is not one position wide, it is two position wide. So yeah, I'm going to write some code now and I will see you in a bit once I have the answer, and then we will compare our notes. Until then, all the best. And yeah, welcome back. We have received another gold star for part 2, and with this we have completed the day 15. Not gonna lie, I thought the problem is much simpler to do than it actually was. It took me around 30 minutes to update my part 1 code to work for part 2. Yeah, if you have to talk about like how I did in the retro, well, for part 2, I started by creating the function to scale up the original map. This function iterated through each cell. So I first thought I will just update it in place, but then I realized it's just much simpler to take each cell and then replace it with this corresponding double representation that was given to us here. Yeah, here I just encoded this thing as a map and then just replaced it while iterating through the original map. And once this was done, the core logic of the simulate function remained largely the same. However, I had to modify the collision detection And there I encountered that there are two type of special cases, because we ended up doubling our map just on one dimension, which was doubling it in terms of the width. There are two interesting cases. So there was a case where our robot would be here and it is moving left or right. And in that case, whenever it is touching a box or moving a box, this case was a little simpler, because if I will find the edge, so if it is going in left or right direction, and if I find the edge, I can automatically find the whole box first, and then in the same direction, I can look for the next cell. And if the next cell is empty, it means that I can move my box by 1 unit. And if it had another edge of the box, I will then, this was a special case where I will take this and then recursively pass to look for the next item. But we always have to look for the next element by 1. And then if we, based on what we find, so if we find a wall, you cannot do anything, you get out. If you find a empty space, well, yes, you can move by 1. But if you find the edge of one wide box, you have to then add a special case to account for the next cell for the full box and then pass it along. But the more interesting case was going up and down, as I explained, because in this case, when your robo is pushing either up or down on a box, it will always be on one half of the white box. And when you do that, you have to look up, like when you have to pass this and look the neighbors. In the left and right condition, I was only looking at one cell neighbor to see like what is the value there. But in this case, I had to write a special condition to look for two neighbors, because now the box, when it moves up or it moves down, it will affect my two cells. And then we had to check the location that, again, the wall condition was easy, that if any of this is a wall, you just cannot move the box. But the box condition was like a whole chain where like you can have boxes that are stacked up together. And I explained that with an example here. But still, writing code for this where the boxes are aligned in this direction and when you're pushing one, it will still go down. And of course, this is a puzzle and it's not a perfectly centered world. So there are no center of gravities and boxes cannot turn. So we have to assume that if you're pushing it in one direction, it will go. So one aha moment for me was realizing that I can represent these white boxes as a list of two tuples, where each tuple represents the coordinates of one of the cells occupied by the box. So that made it very easy for me to check for the collisions and update the box position. And yeah, with this, I ran the code first for my test case, and then when the test case was done, I ran it for input. And finally, for GPS coordinate calculation, I just modified my function from part 1 where I was finding the initial box. Here, I think we were given that it will always be from the left edge and the top edge. So I just looked for all the left angular brackets and calculate the GPS function on that. And once I got that, we got the answer. And with that, we have completed that, and we have received 2 stars for day 15. But with this, folks, we are at the end of day 15. I hope you had fun enjoying the problem. And if you are still confused with the part 2 approach, I'm going to push my code below in the GitHub repository. Feel free to check it out. And if you think you can make some enhancements, I'm very happy to review some of the pull requests as well. And yeah, with this, I will take your leave and happy coding. Bye-bye.